Okay, so I want to welcome everybody to the course, to Logic Control. I want to go over the syllabus in just a minute, but what I want to do is have you guys send me attendance by texting me a number. We'll do that at the start of each class. So there's a number here. You might want to just save it in your cell phone, 513-494-6162. What I need for you to do is go ahead and get your phone out right now. Text me at this number. In the body of the text, you want to write Logic Control, and then in the body of the text, you want to write your first and last name. So go ahead and do that now. We'll do that at the start of each class for attendance purposes. I'll give you a few seconds to do it, and then we will start. And I'm just going through to see, I don't recognize any of the names. Some of you might have had me for the circuit analysis course, but none of these names look familiar, so maybe I didn't have you guys, I don't know. All right, so as you can probably tell, I'm not using Zoom, I'm using the old Collaborate from our Blackboard system. And what you can do, you want to make sure that you, when you log into the class, that you have your mic muted. The way this system works is that when you unmute your mic and you start to talk, it'll cut the camera away from me onto you. And if you have your camera open, then it'll go to your camera. If you don't have it open, it goes to an icon, an empty icon. I do invite you to open up your camera if you want to. You don't have to do it, but sometimes from my end, right now I'm looking at a camera, I'm talking to a camera, and I'm actually used to being in front of students, so it kind of feels better when I see faces, but again, I'll leave that up to you. So what I want to do to start is I want to go over the syllabus. Now, if you're not familiar with this system I'm using, there is when I share this document with you, there is in the upper left-hand corner, right up under the hamburger menu, there's a little magnifier. You can click on that, and you're able to zoom in and out on the document. I think you're able to scroll up and down, and you're also able to click off the document. If I have my camera open, you can go back to the camera at any time. So right now, you should be looking at and viewing the syllabus. If you haven't had me for other classes, my name is Ron Singleton. You can call me Ron. My email address, this is my personal email address. I know some of you email me through the UC system, which is okay. I have a couple emails that I use. It's kind of hard to keep track of things, so I kind of, when I can, refer students to my personal address. If you do that, if you use that personal address, just make sure you put UC student in the subject line. It'll go to a folder that I have set aside especially for UC students, and then I'll see it. Again, if you want to use a university system, I'm okay with that. I just don't check that as often as I should. The best way, if you need to get a message to me, is you'll see there's a number you can text, the same one you use for attendance. I do not have a cell phone. If you text that number, what you're texting is, if you're familiar with Google Voice, I have a Google number, and that serves as a kind of like a cell phone for me. You can text, you can send pictures, pretty much the same thing you can do with a cell phone. So if you have to get a hold of me, you have 3 ways to do it. The best way or the fastest way is to text me at that number. You can text anytime you want. If I'm not available, I just won't answer your text until I see it. You can also email me at my personal email, or you can use the UC system. I just won't see it as fast as if you text me. Of course, the meeting times, you're all here, so you know it's Monday, Wednesday, Friday from 1 to 2, and of course, this is a online class. Usually office hours, what I did in the past since we've been doing this online stuff, we need to talk about anything, usually I'll try to get in here 15 minutes before the class starts, and I'll open up the camera. That doesn't always work out for me, so definitely after class, if we need to discuss anything, I can stick around for as long as I need to stick around. Pretty much free after this class. So if there's something that comes up, something we need to talk about, we can do it through the camera. There's a whiteboard with this system. We can share documents, and if that doesn't work, if we have to meet face to face, I am open to doing that. I'm not actually on the campus. I'm close to the campus. So if I do need to meet face to face for any reason, that's not an issue at all. Just let me know. I've been teaching this course since 1999. And back in those days, we actually had two separate colleges. There was the College of Engineering and there was the College of Applied Science. And I was with the College of Applied Science. And during those days, our college was located on Victory Parkway campus, where I think some of your labs are still located. And at that time, we had an actual PLC lab with the equipment set up, a conveyor, actual hard wired PLC. And at that time, I shared the class. I taught the theory for years, and there was a professor by the name of Mark Fassler who taught the actual lab part of the class. It was a split class. Well, since we've combined years ago with the College of Engineering, we don't actually do a hands-on physical lab anymore. So what we do is we use simulation software. So there is no textbook that you need for the course. I did away with that back in 2004. However, there is two pieces you need to buy. You need to buy the simulation software, and then there's a lab manual that you can buy, or maybe you might be able to download it. Now, up until about 3 or 4 years ago, I used to order the lab manual to the bookstore, the UC bookstore, and then the students would go to the bookstore and they would receive the lab manual. But the bookstore kept going up on the price. The price just got outrageous. So kind of took a vote on it, and I decided one semester that I asked the students if I should order it or if they wanted to just get it offline and save money. And of course, 100% of the students decided it would be better or more beneficial to save money and get it offline. So you won't find this lab manual in the bookstore. However, it is available online wherever you buy your online books, and you can get it. I've seen it as cheap as $10 and as high as what you would pay for it in the bookstore. Now, the way this class is going to work, we will have 5 weeks of theory or lecture, and then we'll have 5 weeks of lab, and I'll explain that in just a second. But I'm bringing that up to say that you will not need the lab manual. Probably, I would say maybe 3 weeks from the day you might want to think about ordering it. If you want to go ahead of the curve and go ahead and get it, you can, but you want to be careful. I actually want to give you a picture of the cover of the lab manual, because the author that wrote the manual actually wrote 3 books, and all of the covers look exactly alike. And so this happened last semester. It happens every semester where a student thinks they're ordering the lab manual, and you're actually ordering either a textbook, or he has another book called an activities manual. So if you're going to get the lab manual right away, I suggest just kind of wait a day or so, and I'll post up on your Canvas a picture of the front cover. You want to make sure that whatever you order, it says lab manual on it. You cannot go by just looking at the cover. You actually have to read it and make sure it says lab manual on it to make sure you're getting the right book. And I'm not sure that the edition, probably any edition will work. I don't think they've changed that much. But I'll have more to say about that later. Again, you don't need that right away. So back in 2004, I got rid of the textbook. I put everything on PowerPoints. And normally, of course, before COVID, this was a face-to-face class. And what I would do is walk in the room. I had the students all get 3-ring binders. I would print out the PowerPoints. I would 3-hole punch the PowerPoints, and I would pass those out in class. And basically every week, I'd hand out a pack of PowerPoints, and we would make basically our own textbook. So now we're remote, but I urge you to do the same thing. Get a 3-ring binder. Of course, I did put everything on Canvas. I laid it out where you can click from one document to the other. But I still recommend downloading the PowerPoints, 3-hole punching those PowerPoints, and putting them in a 3-ring binder. It just makes studying for quizzes and exams a little bit easier. Speaking of quizzes and exams, the next part of the syllabus, you'll see the list of items that are graded. There will be a quiz every week. There's homework, and there are 4 exams. Each exam is worth 15%. There's no final exam. All the exams let's say exam, the last exam is really more like a project. There's actually, let me explain the way, there's not actually 4 exams. There's 4 things that I call exams, but you actually have 2 written exams. You'll have your first exam, which is a written exam. You'll have your third exam, which is a written exam. But then exam 4 is a project that you'll do, and exam 2 is a program that you'll do. So there'll be 2 written exams and then a project and a program. And I'll say more about that when the time comes near. Now, the way things are kind of scheduled here, we'll do the first exam maybe in about 4 or 5 weeks. We'll have that first exam, and then you won't have an exam for a while. You'll do exam 2 again, but that's a program. But the other 2 exams will be kind of towards the end of the semester, and it'll seem like we won't have enough time for it. But don't worry, we'll have plenty of time for everything the way it works out. I just think just kind of follow the flow of the class, and then you'll be in good shape. Sometimes I get students that get a little concerned because we've only had 2 exams, and it's kind of, we have like a week or 2 left in the semester, and then they're worried that we won't get everything done. But just remember, you only have 2 written exams. And again, I'll say more about those exams as the time nears. And quizzes, I don't have any makeup quizzes or exams. Everything is online. Now on the syllabus, it says that I'll give the quiz on Fridays. And I think I did that back in the summer, where at the beginning of the class on Friday, I would give the quiz, and then I would start class. But it kind of worked out well last semester that I just kind of set the quiz up to where you can take it between Friday evening and Sunday night. You can take it whenever you want, but once you click on it, they're all time. You'll have so much time to take it. And I think that kind of worked out. So I think here it says you'll be given, somewhere it says you'll be given quizzes on Friday. I think I'm going to stick with just kind of opening up the quiz on the weekend, and you can do it anytime before the midnight. The deadline will be midnight on Sunday. And, they're usually maybe 10 minutes or so. It doesn't take long. It's just usually multiple choice or some kind of true false type of situation. So you'll be able to click on it, take the quiz, and be done with it. So I'll leave that open. If I decide to give the quiz on Friday, I'll let you know. Pretty much just kind of look forward to having those quizzes available to you over the weekend. You can take it anytime between Friday evening and late Sunday night. And if anything changes, I'll let you know. So the rest of this you can leave. You can read for yourself. Again, I teach this course, this circuits course, and I was looking through the list of names. I don't recognize any of you guys, so I'm not teaching that course anymore. So I don't know if I had any of you before, but if you had the circuit analysis course from UC, it would be helpful, but it's really not required because I do a lot of review. I go over things in pretty much detail. So I do have students without an electrical background take the course and do very, very well in the course. So if you don't have that, it's not a big deal. Course content, you can kind of read that yourself. This is kind of what we'll go through. Now this next page is the layout, the way the course is structured. And you'll notice that I have what I call blue weeks and red weeks. So blue weeks and red weeks. On the blue weeks, we'll meet every Monday, Wednesday, and Friday from 1 to 2. And on the red weeks, starting June 15th, that's when you'll have labs posted to the internet and you can do those labs. And the idea is that you'll, the time that we would have been in class on Monday and Wednesday, that 1 hour, you can use that time to work on your labs. Now, you don't really have to do it during those times, but basically during those red weeks, we're only going to meet by video on Fridays for 1 hour. And during that time, if I want to give a quiz, I can give a quiz. Sometimes I'll go over material. I can answer questions. It just depends on where we are in the course. But just be aware that on those red weeks, then we only meet once a week on Fridays for 5 weeks. And then the idea is that the Monday, Wednesday time that we would have met, you can use that for lab. Of course, you can do the labs anytime. The labs aren't that, I mean, the first one is pretty simple, the first couple. The others will take you, plan to spend maybe a couple hours on them. but they're not really that difficult. So make sure you take a look at this, and then at the bottom, there's a couple holidays this semester. There is Memorial Day coming up, May 25th, and then there's Independence Day, which we celebrate on, well, it says July. Oh, I didn't update this. So these dates are wrong. I don't know why I didn't update that, but I'll update that. I thought you guys had the new syllabus, but I think online it actually is updated. If not, I'll take care of that. But the point stays the same, is that on there's Memorial Day, and then there's Independence Day, which we're celebrating, I believe, on July 5th. So I don't know if this is updated or not on your Canvas. I'm pretty sure I took care of that, but I'm looking at this. It says summer 2020. So some kind of way I pulled up an old syllabus, but I think you have the right one on your Canvas. I'll check that out, and if not, I'll correct that. So that is the syllabus. Does anybody have any questions over anything that I mentioned so far on the syllabus? Any questions or comments? All right. Okay, well then I'm going to move away from the syllabus. And okay, great. Thank you, Ethan, for opening up your camera. The rest of you guys are still, I guess you're scared. You don't want me to see what you look like. So I invite you guys to do that as we progress through the course, so I can see that I'm talking to actual people instead of this camera. So let's talk about the course. Let's get into some material here. So the name of the course is Logic Control. Now I'm assuming you sent me a text, so make sure you sent the text to 494-6162. We'll get rid of this to make some space on the board. And the name of the course is Logic Control. Logic Control. So why did they name the course that way, and what exactly does that mean, Logic Control? So logic, and when I say logic, electrical logic, logic means that we're gonna make decisions based on a set of predefined inputs. So we're gonna actually get electrical circuits to make decisions based on a set of what we call predefined inputs. And a predefined input, what that is something called the truth table that we'll talk about. So we're going to make decisions based on inputs. Now these inputs are what I call real world inputs. So there's some kind of signal that we'll look at, that we'll read, and depending on the state of those signals, we can make decisions. We can make certain decisions. We can make certain logical decisions, and there's three basic types of logical decisions we can make that we'll talk about in just a second. So logic, making decisions based on a set of predefined inputs. And then to control, what are we controlling? Well, we can control a simple machine like a motor, or we can control a whole industrial process, like maybe a factory where you're doing some kind of assembly. We can control something small, we can control something large. But in general, you kind of already know what that term means. To control, you can turn something on, you can turn something off. Those are the simplest types of control. You can do that with a single switch. You can speed a motor up, you can slow it down. There's a whole lot of ways we can get a machine, device, or process to change state, and that's what we mean by control. So we put the two together, we can make basically electrical circuits make decisions to tell us when or how to do these things over here, these functions. So how do we do that, and what exactly do we mean by input? So let's talk about that. So to understand how this is done with electrical circuits, we have to start with two simple ideas. So let's talk about this. What's the difference between a switch and a button? So we got a switch and a button. What's the difference between the two? Now you guys, you can open your mic, you can answer, close your mic, and then we'll move on. But just make sure you close your mic when you're done talking. So who can tell me what's the difference between a switch and a button?
I think a switch is like when it's pressed, it triggers like a condition is set, and it's like button is like instantaneous. I'm not too sure.
Okay, well, that's a good guess. But I want a physical description though, not how they act, but give me a physical description. Let me turn the volume up because I'm having a little bit of a time hearing you.
So I think that like switches specifically apply to PLCs. Like on my previous co-op, I think I saw like what an old switch looked like back in the day, and like when I think it also works with like a coil too. I'm not exactly sure, but I think that like once a switch is pressed, it's like two things make a connection and then like electricity flows. That's what it
Okay,
used to be, but I think that now the definition changed a little bit and like how it's actually applied.
so give me an example of a simple switch that you've used probably today.
I guess like a light switch.
Yeah, light switch. Everybody's using a light switch, right? You walk into a room, you have to mechanically move something, and by moving, you can turn the light on or off. But by that mechanical motion, either opens or closes a electrical circuit. And the way we describe that is we say it either makes or breaks contact. So we kind of we all know what this is. You guys are looking at the camera, you're looking at me. I got one person talking, but you really know what this is. You've all used switches before. What about a button? How is a button different than a switch? How does it differ? Or give me an example of a button.
I think it's like kind of similar, but it would send like one signal instead of like completely changing like how a circuit flows.
So an example of that might be like say like a doorbell, right?
Yeah.
So if you walk in your room, I don't know what kind of switch you have on your wall, but you can flip that little lever, you can flip the switch to turn the light off or on, but you can press the button for a doorbell. You can press that button as long as you hold that doorbell down or the button down, then the doorbell will make a noise. Now this is simple, guys, but it really is important. And everything we're going to talk about this semester starts right here. So let's look at a switch, a simple switch. And so a basic switch works like this. You have a part that moves. So you have a wire, and then you have this part that moves, and then you have another part over here that they can connect to. There's a wire coming out. So a basic switch, the most basic switch looks like that. And what happens is you can push this switch down. If you push it down, then this is a conductor, this is a conductor, this is a conductor. So if you close the switch, that is if you make contact, then it goes from this state to this state. And as, I don't know who that was talking a minute ago, but as they said, now current can flow in the circuit. So right here, this switch is open and this switch is closed. If I have a closed switch, current can flow through it. If I have an open switch, no current can go through it. There's an open circuit there. Now, when you move that lever that we talked about, let's say you got the type of light switch on your bedroom wall, you have the lever that you move up and down. That thing that you move up and down, that thing is called a pole. P-O-L-E, a pole. And when you pull the lever or you push the lever, when you move that pole from the open position to the closed position, you make contact. Well, the thing that the pole touches on the other side, that's called the contact. That's a contact. Now, you can name the switch by the number of poles you have and the number of ways you can move the pole to make a contact. That's important. You can name the switch by the number of poles you have and by the number of ways you can move the poles to make contact. So like right here, the way I have this, I have one pole. So that's a single pole. And I can only move that pole one way to make contact. I can move it from the open position to the closed position. So if I was going to name that switch, you start with the number of poles. So this is a single pole, and I can only move the pole one way to make a contact. When you move the pole to make contact, that's called the throw. Like you throw a baseball. I can only throw this one way to make contact or to break contact. This is a single pole, single throw. So if I name that switch, I call that a SPST. Single pole, single throw. If you go to the switch store, if there was a switch store, and you ask for SPST, they know exactly what you're talking about. But I don't have to do it that way. What if I did this? What, instead of doing that, what if I had it like this? What if I had a contact here? I had a contact here, and I had a pole right here. So now I got 3 wires I can connect to. I can connect here and here. My main wire is here, and I can. How would you name that? What would you call this? How would you name that?
A double pole, single throw.
So the pole is the part that moves, right? It's the part that moves. So I have one of those. So like here, that's a single pole. So I got a single pole, but I can move it either to the left or to the right. I can throw it 2 ways. So that's a single pole, double throw. So again, if there was a switch store, you could go to the switch store and ask for a SPDT. They know exactly what you're talking about. Or maybe I want to do this. Instead of doing that, what if I do this? What if I have, basically I put 2 of these together. I have this, and I have this. And when you see this, you'll usually see between these, you'll see a dotted line like this. And what this means, a dotted line means, is that when you move one of those poles, both of those poles move together in the same way. So now I have what? Well, I have 1, 2. I got 2 levers. I got 2 poles. So I have a double pole, but I can only move that one way for both those poles to make contact or break contact. So it's a single throw. So I can play this game for a while. There's a lot of ways you can configure this, but you basically count the number of these you have. That's the pole, and you count the number of ways you can move the pole to make contact. That's the throw. So that's something you could think about, and you want to be able to do that. So I want to start with this one though. This is the simplest switch. We're going to use that to help build our logic circuits. But before we do that, let's look at the difference between a switch and a button. Now, a button, we gave the example of a light switch, like you might find in your bedroom to turn a light off or on. And for a button, I gave the example of maybe like a doorbell. So the way that is constructed, there's actually 2 sets of contacts inside that doorbell. And there's a wire here, and there's a wire here. And I'm going to go ahead, just so you can see, I'm going to draw a whole circuit. I'm going to draw a voltage source, which, as you remember from your circuits course, that's a battery. And I'm going to draw maybe I got some kind of, let's just say a light that I got hooked to this. So I got my power source, and I got a light. Now this button, I have a contact here and a contact here, and then I have the actual pole, which goes across like this. And then there's usually some kind of point under it. I can press that down. When I press it down, then what happens is that pole is a conductor. When you press it down, it basically makes contact and bridges that gap right there. Now current can flow through that pole over to the other side, and I have a closed circuit, and the light bulb would light up. Now, there's something called a device or switch being normally open and normally closed, and that's important. So I want to talk about this. You know, for the way a doorbell works is when you press it, as long as you have it pressed, the doorbell's ringing. When you release it, it turns off. So what they have here is a spring. Imagine a spring right here. I have a spring, and that spring is pushing up on that contact, keeping it separated. The only way to get the contact to touch, or the pole to touch the contact, I got to press it. And so when I press it, current can flow through, but when I release it, the spring is going to separate the poles from the contact. So if I took the switch and I laid it on the table, I took it away, and just laid it on the table, I didn't touch it at all, and that spring is separating the contacts from the pole, we will call this a normally open push button. When I say normally open, I mean in a state where there's no human interaction at all. If you just lay the thing on the table, the contacts are open. And so if you're going to name this switch, you would call this a normally open push button. So again, you can go to the switch or button store, you can ask for NOPB, they'll know exactly what you're talking about. You need a normally open push button. A doorbell is a normally open push button. But I don't have to do it this way. I can do it like this if I wanted to. Suppose I constructed the button so that I did this. I have my contacts, but this time my pole is on the bottom, and the part I press comes up like that. So I can press this down, and when I press it down, it actually separates the pole from the contacts. And then this spring right here, what I have is the spring on the other side. The spring is right here. And again, it's pushing up on that contact. In this case, where this spring is keeping the two separated, the way I have this one is actually keeping the contact and the pole together. It's keeping it closed. So if I lay this on the table, the normal state of that push button is closed. No human interaction. This is closed. So how would I name that? I call that a normally closed push button. So I have a single pole, single throw switch. I have a normally open push button. I have a normally closed push button. So back in the old days, in the beginning of this logic stuff, when they wanted to make circuits make decisions, this is the kind of stuff they use. They use actual physical switches and actual buttons. So how do you do that to get a circuit to make what I call a decision? So let me introduce you to the three basic logic functions that we're going to talk about and see how to use these switches. Now, for now, you can think of, when I talk about an input, you can think of a switch or a button. When I talk about an output, you can think of whatever it is you're controlling. Here, on the circuit I just erased, that output was a light bulb, but it could very well be a motor. It could be whatever it is you want to turn on or off for this circuit. So, when we talk about logic, there's three basic logic functions, three ways we can logically wire an electrical circuit. Three basic ways. Now, there's other more complicated ways, but any other logic function we talk about is just a combination of what I'm about to show you. So, there's three types of logic. Here's what we call AND logic. A-N-D. So there is AND logic. There's OR logic. And then there's NOT logic. So AND logic, OR logic, NOT logic. So I'm going to look at each of these as a circuit to represent each of these, and then we'll kind of expand on this as we go along. So AND logic. Now, what you want to kind of get used to, guys, is that these words in English have certain meanings. They have certain meanings, and the meaning is defined by what we call a truth table. And let me show the circuit. Let's look at how the circuit works, and then let's look at the truth table to understand electrically when I say AND, what am I talking about? An AND circuit. So a basic AND circuit works like this. You take, this will be a 2-input AND. So remember, when I say input, it's a switch or a button. A 2-input AND. So I'm going to draw a circuit. I'm going to have two switches like this. So I have two inputs. We'll call this input A, this input B. switch A, switch B, whatever you want to call it. And then what I'm going to have over here is a power source. So don't remember from the circuits course, again, this is your symbol for a battery. There's a power source. And over here, I got something I want to control. Again, a light bulb. So I'll just have a light bulb. And what I want is, I want the light bulb to light up. I think a current flowing through the circuit, it makes this a little simpler to think about. But if I want that light bulb to light up, what do I have to do? What happens?
Do you have to close both switches?
I have to close both switches. So we're going to make a table. And this table is going to, from the table, we're going to look at whether, we're going to show all possible combinations of the switches. Switches can be open, closed, or any combination. So I'm going to show what that looks like. So the way the table is constructed, you'll always show your inputs on the left side of the table and your output on the right. So this light bulb right here, we call that L, so I'll just call it L here. And I have two switches and two inputs. You got A and B. Now, if my switch is open, instead of writing the word open, I'm going to use the word false. And if my switch is closed, I'm going to use true. Matter of fact, I'm not even going to write the words out. If my switch is open, I'm going to use F for open. I'm going to use T for close. Now, we're only using that for today. Actually, we use a system called binary, and we'll talk about what that is. But everything is really based on zeros and ones. But for now, we'll use true or false. False is open, true is closed. So in this table, I'm going to show all possible combinations of the two switches. So there are all the possible combinations. I can have both switches open. I can have the first one open, the other closed. I can reverse that, or I can have them both closed. And as somebody correctly stated, looking at this circuit, the only way to get that light bulb to light up, the only way is when both switches are closed. When this row right there is true, for all other combinations, my output is false. So this table right here represents AND logic, and this is the truth table for AND logic. So simple circuit that you probably use but probably didn't think about it. You know how when you go in your car, you get in your car, you stick your key in the ignition. Now, I know you have the keyless things now, but let's say you actually have a key you put in the ignition. When you stick that key in the ignition, there's a little micro switch in the ignition or an optical sensor. And when that key goes in the ignition, it actually makes contact with the switch. And it changes the state of that switch. Let's say it closes that switch. So if you have the key in the ignition and you have your door open, the buzzer rings on your car. That's an AND circuit, a very simple AND circuit that you can simply wire up like this. If I wanted to, if I wanted a 3-input AND, I could simply add another switch, but then my truth table becomes bigger. And we'll talk about the truth table in another class. But this is basic AND logic, and what you got to remember, if you want the kind of logic where you got to have two or more conditions to all be true in order for something to happen, some output to turn on, off, or whatever, then you want to use AND logic, and this is the truth table for AND logic. This is actual definition of AND logic. When I say AND logic, you think that truth table. Well, if I wanted to, I can do this. Instead of taking the switches and hooking them up like that, I can do this. I can rewire this to where I have my power source. And I got my two switches. I guess I drew the light bulb like this. But this time I'm going to take the other switch and put it, now if you remember your circuits, before I had the switches in series, they were kind of end to end. Current had to go through one to get to the other. But here I have them hooked in what you will refer to in your circuits class as parallel. I got these two switches in parallel. So again, I got switch A, I got switch B, I got my output, and I got my power source. Now, of course, you can see right away that this is a little different. For this one, if I close switch A, current can follow this path, light bulb comes on. If I open A and close B, current goes through this path, light bulb comes on. If I close both switches, current comes and splits through both switches, again, the light bulb comes on. Matter of fact, the only way not to get the light bulb to come on is both switches have to be like they are right now. Both switches have to be open. But if one switch or the other switch or both are closed, then the light bulb will light up. I have an output. So this is a basic demonstration of what we call OR logic. OR. So what would the truth table look like for OR logic? So again, I show my inputs. I show all my possible combination of the switches. And I say, okay, well, when will that light bulb light up? If any switch is closed or both switches is closed, I get an output that is a light bulb lights up. The only time it doesn't light up is when both switches are open. So this output is going to be true, 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 and it's false right there. Now, if you look at this, this is the opposite of the AND. This was false, 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 true, and this is false, true, 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 or logic. So in English, what we mean, when I say English, electrically, what we mean, when you say to an electrical engineer who's using logic, this and this is what you're talking about. You mean where both conditions are true in order to get some kind of an output. But when you say or, then you're saying that either one condition is true or the other condition is true, or both could be true. And that will represent OR logic. So this truth table, this is the very definition of what we mean by OR logic. When I say OR, you think that truth table. So we got AND logic, we got OR logic. Now, NOT is a little hard to wrap your mind around at first. So I'm just going to show you how a simple NOT circuit works. Don't ask any questions about it because it's going to make sense later on. But to represent a NOT circuit, NOT, you got to use a normally closed push button. So a NOT circuit is like this. I'll just change this one. So for a NOT circuit, you would use a normally closed push button. And as long, let me just write it out. So the way to think about this is the state of that push button, it can either be not pressed or it can be pressed. If it's not pressed, then your output is true. If it's pressed, then your output is false. Because if you press that, then what's going to happen is you're going to move the contact away, or the contact, the pole away from the contact, going to separate it, and then the light bulb will go off. So for now, just think of your NOT like this. And again, this will make sense later on because when we actually get to where we use numbers, they call that NOT circuit an inverter because it inverts your inputs. But I don't want to get into that right now. But here's what I do want you to know. If you have just basic control you want to do, if you got some situation where you need two conditions to maybe turn a light bulb on or a motor, you want to use this logic. You can extend it to 3 inputs or however many you want. But if the logic you want is if one condition is true or the other true or both true, then you're going to use this. And then sometimes you want to use NOT logic. Well, most situations you're going to be faced with, or that they were faced with back in the day, is way complicated than this. So then what you can start to do is you can imagine how complicated this will get. You can start hooking AND circuits and OR circuits and NOT circuits together to control some kind of really complex process. And you can imagine it's a wiring nightmare, but that's what they did back in the day. One thing though, it doesn't really do you much good to have an automated system where if you got to have a person moving the lever of a switch to turn something off or on, that doesn't work for us. So we really, even though we think about switches when we think about and logic, or we think about buttons when we think about a NOT circuit, really what they use is something called a relay. A relay. So I want to talk about that, what that is. I'm starting to get out of time here, but I want to close by talking about this device called a relay. Now, has anybody ever heard of a relay? And if you have, what are they used for? What is a relay? Anybody ever heard of a relay?
At least when it can you hear me?
Yeah, I can hear you.
At least when it comes to cars, it gets sent an electrical signal and closes a circuit.
Yep, that's exactly right. So I see them, if you open up your car, sometimes they have the fuse box outside on the engine, and you open it up, and you'll see the fuses, but then you'll see a big square plastic thing, and you can pull it out, and it has these little connecting points. You can plug it in. That's a relay. I don't think they do it anymore, but back in the day, you would put driving lights on your car. You can buy that. It wasn't original equipment. You can go like AutoZone and buy some fog lights or driving lights and actually wire them into your car. You mount them on the bumper, but you would have to use a relay to turn those switches off and on. So what a relay is basically a switch, but it's an electromechanical switch. I want to talk about how that works. Now, your first quiz is going to be over relays. So that's coming, I think it's set up. I'll set it up to where it's available to you on Friday, and you'll have the whole weekend. But here's what that first quiz is. There's this video. This guy does a beautiful job talking about relays. Best I found on YouTube. So you're going to watch this video on relays, and then as soon as you watch it, I want you to take the quiz. So I think the video is maybe like 20 minutes long. So make sure you have time this weekend when you take quiz 1. Watch this video. Don't try the quiz until you watch the video. Watch the video. Take notes. Write down some stuff. Pay attention to what you're writing. And then as soon as you watch the video, go ahead and take the quiz and answer the questions. I think it'll be pretty simple. But he does a good job. I'm going to do a basic job talking about relays, but he does a much better job than what I'm going to do right now. So what is a relay? Well, I don't know if when I was in high school, I think, probably junior high school, my teacher took a nail, an iron nail, and she wrapped a coil around it, a wire, and then she hooked it up to a battery. And then we were able to pick up paper clips with that. This is called an electromagnet. Now, I don't know if they still do that in the schools, because I've been out of school for a long time, but if you haven't seen that before, maybe when we're done talking, when you're bored, go to YouTube and just put in basic electromagnet. But basically, you can take any kind of metal, not any kind of metal, it works best with iron, soft iron like a nail, and you wrap a wire around it, and when electricity flows through it, associated with anytime current flows, there's always a magnetic field when there's current flowing. So if you have a wire, a current carrying conductor, there's a magnetic field around the conductor, which is caused by the flow of current through the wire. So the effect that coiling that up has, it makes the magnet stronger, the magnetic field stronger, and the iron will concentrate it to make it really strong. So where you have a permanent magnet, like the one you put on your refrigerator to hang up pictures or whatever you use them for, that's a permanent magnet. An electromagnet is one that if I have a wire, a coil around they call this a core, a piece of iron, as long as I have, say I put a switch on here like this, well, that switch is open, then this thing is not a magnet. If I close it, then this nail is magnetized and I can pick up paper clips. Well, I don't know if you had me for circuits. I don't know if you had me for circuits, but if you did have me for electrical circuits, then in that class we talked about something called resistance. And basically, if I have wire, The longer the wire, the more resistance I have. And the thinner the wire, the more resistance I have. So from that course, you talked about resistance, and then there was this thing called Ohm's law. Ohm's law says that current is equal to voltage divided by resistance. So what they do is when they make a relay, they take a piece of metal. It's not a nail, but they take an little iron thing called a core. Then they wrap wire around it. They wrap a lot of wire around it like that. And the reason they do that is they want the resistance of this coil to be really, really, really high. Resistance of wire is directly proportional to the length. So if I have a long piece of wire, I got a high resistance. They wrap a lot of wire, or thin wire, around that core to give it a really high resistance. Why they want a high resistance? Because they want a really low current. High resistance means low current. So now let's make a relay out of this. So what we do to make the relay is actually quite simple. We take the coil. Imagine I have a coil. I'm not going to show the core. I'm just going to show the coil. So I got the coil, and I got that hooked to a switch, and maybe here's my voltage source. Now remember, I got a lot of wire here, so that's a high resistance circuit. When I say something is a high resistance circuit, what I'm really saying is this is a low current circuit. When I close this switch, the current flow in a typical relay coil is on the order of milliamps. A milli is 1,000th of an amp. So we're talking about thousands of an amp flowing in this coil. But when I close the switch, there's a magnetic field around the coil. When I open the switch, the magnetic field disappears. So now imagine that I take a single pole, single throw switch, and I put it like this. I got the switch like this, but on this switch I got a really weak spring, metal spring, forcing this up that way. That's a spring. So now what happens when I close this switch over here? This switch is closed. Current flows through the coil. And current flowing through the coil causes a magnetic field around the coil. And that magnetic field is strong enough to pull the pole down here to get it to engage the contact. As long as I close this switch, then the magnetic field is going to close this switch. Now you might be thinking to yourself, well, okay, well, what good is that? What good is that? We're using two switches when we could have used one. But remember, this is a low current circuit. We're pulling thousands of an amp here. We're pulling milliamps in this circuit. This single pole, single throw switch here, that can be as big as we want it. So this can actually handle an amp. It can handle 100 amps. In theory, it can handle 1,000. It can handle as much current as we want. The bigger the pole and the contact, the more current this can handle. So basically what I have is a device where I use a small current to control the big current, and you got to be clear. Notice that the coil circuit and then this contact circuit, they're two separate circuits. I'm just using one to magnetically engage or disengage the other circuit. Now you use this all the time. Anytime you want to use a small current to control a large current, you're going to probably do it with a relay. Perfect example of this. Think about the way you start your car. When you start your car, when you turn that starter motor over to get the engine, you got to get it spinning so that when you ignite the fuel, it's got to already be moving, right? So when you turn that starter motor over, you're probably pulling around maybe 10, 15 amps. Now that doesn't sound like a lot, but 1 amp is a lot of current. We usually deal with milliamps. A little over 100 milliamps is enough to fry you. Voltage doesn't kill you, current kills you. Doesn't take much. 100 milliamps can stop your heart. So when you get into talking about 1 amp or 10 amps, 15 amps for a starter, that's a lot of current. It's a whole lot of current. So there's no way, if they had one switch to control that starter, the more current a wire is going to have flowing through it, the bigger the wire. You'd have to have the whole battery cable coming up through your steering column if this was your key switch, to engage your key switch. You don't want to do that. So what you have, when you turn the key switch, you're actually engaging or disengaging this low current circuit. And then this contact here is either outside of your starter or sometimes it's in the starter. But when you turn your key switch, you're turning this and that coil circuit of a relay, a low current circuit, and you're controlling this. Your actual starter motor in your car is hooked here. You got your battery, and then you got your starter motor. And so when you turn the low current circuit over here, your key switch, magnetically it pulls this down and engages your starter as long as your key switch is closed. The point I'm making is a relay does two things. Number one, I can use a low current circuit to control a high current circuit, but more importantly, I don't have to be here to push this button. I mean, here I do on the board, but there's no reason why I can't take a computer and have it open or close a switch, or push a button on your cell phone and have it open. I can make an electrical device open and close this relay, open and close this switch. So earlier when I was talking about AND circuits using switches, they really don't use switches. They really use what we call control relays. So it's the same kind of thing. Instead of hooking up switches, they would have these relay contacts in series, or they have these relay contacts in parallel to make your AND OR logic, but then it would be electrically controlled by some kind of device. Instead of having a physical person here, I have some kind of computer opening and closing the switch right here. It's not really a switch. It's more of the presence of a voltage or absence of a voltage can cause this circuit to open or close. And so I don't know if my picture was good, but I did make a copy. Oh, let me show you. So on my relay, now remember, this is two separate circuits. I have the coil circuit. This is the coil. That's the low current circuit. This is a totally separate circuit. It's just engaged magnetically. But there's a spring right here keeping that contact up, and when I close this switch, the magnetic field pulls this down. So if you just look at that switch right there, we just look at it, that's a single pole, single throw a button or switch, but it's normally open. This spring is keeping this thing open, so that's actually a normally open switch. Before we talk about a normally open push button, here's a normally open switch. Now the only reason I'm bringing that up is the contacts here are named. Let me get rid of the coil. This contact here will be called the normally open contact. The normally open. So if I lay this relay on the table, no power connected to it, this spring is pulling this pole up away from that contact, and so we say that is in this normally open state. But there's no reason why, if I wanted to, I can actually take another contact and put right here and bring a wire out. So often what they do with relays, they'll have more than one contact. Now, if I lay this on the table, I'm making contact with this one, but not making contact with this one. This will be my normally closed contact. This is my normally open contact. And so it gets a little kind of cumbersome drawing it this way. So what they'll do, and what we'll do in this class, is that when I want to draw a relay contact, I'll draw it like this. That's a relay contact. And as a matter of fact, this is a normally open relay contact, so that will represent that one. If I want to show this one, the normally closed contact, I just put a line through it, and I'm talking about that. But what they did back in the day, they would wire these contacts in series to give you AND logic, or in parallel to give you OR logic, or a combination to give you some kind of complex logic function. Now, I'm running out of time, guys. I'm over, but let me just show you real quick. Here's an actual picture of a relay. I think I have it up on your canvas, but right here you can see this is the low current circuit I was referring to, your coil. And so you would put power down here. And then notice you have this spring right here, and the part that moves up and down, the part that I call the contact, they call the armature, and you got these contacts over here. And so you have this is your normally closed contact, because this spring, I don't know, the way this works doesn't make sense, but the normally closed contact, that spring would be pulling this up there. If this was laying on the table, then this contact on the armature will be against that normally closed contact. And when you power this up, the magnet pulls this down and it closes the normally open contact. So this is what they used to use back in the day. Well, we don't do this anymore. What we use now is something called a PLC, a programmable logic controller. I'll have more to say about that on Wednesday. But basically right now, a PLC is just a heavy-duty computer used to replace these relays and switches to give you what we call control logic. So guys, sorry I went over a little bit and I had to rush towards the end. But does anybody have any questions or comments for me before we sign off? And Colin and Ethan, thank you guys for opening up your camera. Aaron, you have a question?
Did you mention that we needed to text a certain number? It's like 494-6162. Is that anything?
Yeah, just for attendance.
For attendance, okay.
Go ahead and do that, guys. If you sign on late, you want to do that every day when we sign on, but go ahead and save this number, 513-494-6162. And then I just put logic control. And then put your first and last name. And we'll do that every day at the start of the class, just so I can keep attendance for the school. Anybody else have any questions? Colin, I like that flag on there. You got a nice background. Beautiful. I love it. And is that a Miller Lite? Ethan's got a Miller. I don't know, Colin. He might have.
Yes, that's correct.
He has beer. I'll vote for the beer.
Hey, I'm pretty jealous of that Miller Lite.
All right, yeah. Okay, guys, have a great rest of the day. Thank you, and I will see you on Wednesday.
That's a nice layup.
Bye-bye.
See ya.